Hey there, Calculus fans. Taking a little break from preparing for the next quarter. I won't be able to make quite as many videos. But I've been making videos on spirographs and art and circular motion. And I was working with my nieces, and it just reminded me of this. I don't know if anyone else did this when you were in grade school or were trying to kill time. This is also just a great little thing to know if you're ever working with kids. You know, just have them draw a set of axes, have them label a few equally spaced points, have them labeled the same 1, 2, 3, 4, have them labeled the same number on this side. Works a little nicer if they have a ruler, but you don't really need it. And then you take this one and connect it to this one. So I don't know if you've seen this before, but you connect these two, and then you connect these two, and with you don't have to have a lot of mathematical skill. You generate a curve. I just remember doing that or seeing that somewhere. So as I was doing this, and I did this with my niece, I was explaining this, asking her if she'd seen it. A natural question is, what curve does this form if you keep doing this with more and more and more of these? That's a calculus question. And I'd never thought about it before. I hadn't really thought about this. I've done this sort of art project with kids a lot. The reason this is called pagan art, or what I remember, like in grade school, is they had these little pieces of wood that had pegs in them, like little nails or something sticking out. And you were given like a big bin of rubber bands, and you had to connect the rubber bands, but it was the same thing. And you got this shape. So I was thinking about it, I was like, well, what is that shape? I'd never seen it before. Now, since I've been working on it off and on here and there when I've had a few minutes over the last couple weeks, I realized it was a root function. When I searched online, everyone says, oh, it's parabolas. Yeah, but but it's like a square root function here. It's a parabola if you rotate it. You know, we would call this a parabola, kind of on its side. But I want to find that equation. And it turns out the function is this. And I'm going to derive this in just a moment. But what I liked about this was, at least the way I did it, which is probably not the best way. I'm not trying to give a polished solution. I'm trying to show you how someone would go about even trying to think about this. Because when I first saw it, I was like, I don't know how they're going to do it. So I want to show you how I was persistent. Not that I was smart, but I was just persistent to like, okay, this has got to be doable. It's got to be some calculus. And over a few days, I figured it out here and there. And I think we can understand this. It allows us to do limits. And I'll show you some visuals at the end. At the end of the video, I'll talk about the errors as well, meaning how far apart these are, because I was really unsatisfied when I finally was done. I then looked at it visually, and I was like, whoa, the error is pretty bad. Even for more, this is only 1, 2, 3, 4, 5 lines. But that error is pretty bad. And I noticed, like, even with 30 lines, the error was pretty bad. And so that made me think my results were wrong. So then I looked at the error term, and it led to some things that have to do with Taylor series. So we're going to hit Calculus 1, 2, and 3 in this course. Calculus 1 we'll need at the beginning. Calculus 2 we'll need when we do the final solving, and Calculus 3 we'll need when we do the errors. So that's why I was like, I got to make a video on this, because I'm going to use all my calculus courses. And again, if you search around, I'm sure there's probably a better way to do this. I'm not claiming to be an expert on this. There's people that have published big papers about this. I just did a quick glance, and I was like, okay, I'm not diving into that. But I do like that I get to do a little bit of calculus here, and I'll probably steal this for calculus courses in the future. Okay, so here's what I thought. I was like, I need to find this intersection, and I need to find a pattern for it. And I'm just going to do a bit of outlining of what I did. There's about 2 or 3 pages of a notebook I filled up with stuff. I first did an example. I was like, what if I just did 1, 2, 5 subdivisions? This is going to be 1/5. This is going to be 2/5. And this is what I encourage my students to do. You have to do an example or two first. I mean, it's great if you can jump straight to the pattern. Sometimes we can do that. But eventually you're going to encounter a problem where you're not going to see your way straight to the pattern. And for some students, that happens sooner than others. But then you should just do an example. Do 2 examples, do 3 examples. I mean, if the problem is really important to you, you're going to do lots of examples. I'm not claiming this is an important problem at all. So what we want to do is find a pattern as n goes to infinity, and n is this thing here. In this case, here's the example with 5. So I knew the first thing I needed to label was that, to think of that as n. Okay? The second thing I sort of labeled was this must be I over n. I being 1, 2. So this is where I start to lose people. Just the moment I write an I or something, it seems that I lose people. But, like I said, if it matters to you. So I realized it was all about finding an intersection. If we just focus on that first one, I need to find 2 lines. So my thought process suddenly became, I know what lines look like. I need the slope, I need the intercept, and I already know the intercept. So the first 2 lines, for example, would be, and I'm going to get through this part fairly quickly, but the first line would look like this with some slope. The second line would look like this with some slope. And then I'm going to find the intersection of those 2. So I don't know what this is, I don't know what that is, but I'm going to find when they intersect, and that's going to be that first point. So I had something x plus 1 equals something x plus 4/5. And I was going to solve for x. And that was my first thought. My other thought is I know a little bit about slope. It might be good to know what this slope is, because as you get closer and closer, that's because of my calculus experience. And at the time, when I was doing the problem, I didn't know what this was. And I tell students, when you're doing a problem with a function, you should always think about the height. That's the function. And that's why it might be good to know where these points are approaching. But it's also good to think about the slope. It's very often, in a given problem, maybe one is more useful than the other. That's the overarching theme in a lot of the calculus problems, is just realizing, hey, we can find both of those, and if we know one, we also know the other, and we can go back and forth. Calculus 1 goes this way, calculus 2 goes that way. But I'm going to use both those skills. So I was like, okay, what can I say about the slope, and what can I say about the values? So here's dealing with the values. Here's thinking about the slope. So I kind of already had some things in my mind forming that were going to help me maybe make an approach to this problem. And when I started this, I didn't think I was going to make progress. And so it was kind of fun that just a few calculus skills popped out and this worked. And again, there's probably a better way to do it. Okay, so at that point, I was like, I better formalize it, because I don't just want to look at one point. I want to look at all of the intersection points, all of these ones along the way. This one and that one and this one at the end. And I want to find those points, then I'd like to think about the slope there. Okay, so the first slope is going to be the slope between these 2 points. And so it becomes pattern finding. So the first slope would have been 1 minus 0 over 0 minus 1/5. So the first slope is going to be -5. Okay, so we have that. The next slope for the next line, which we said is going to go through, and I'm not writing down all the pieces because I'd like to write this down in generality, but the next one's going to go for these 2 points. So that's going to be 4/5 minus 0 over 0 minus 2/5. And you should see that it simplifies a lot. Okay, at that point I was ready to move on to notation and say, what is the pattern for these lines? Okay, so for a given line at a given I value, think of this as I equals 1, I equals 2, I equals 3. I started to see that, okay, the corresponding point is going to be what? So when I is 1, we go all the way up. So we had to somehow connect. So the one challenge I had right away was, okay, what are the points I'm trying to deal with? 1/5, 0, and 0, 1. I feel like I'm spending too long here, but this was really the challenge. I don't want to... Textbooks always jump past this point, and I feel like this is where the challenge is. Once I got humming, then I knew what to do. So I wanted to connect these 2 points, 0 and 4/5. I wanted to connect these 2 points, 3/5, 0 and 0, 3/5. So the question was, what's the pattern that connects these two things? And basically I was like, well, shouldn't we just subtract? But then I saw that didn't work, because if you subtract, this gives you 4/5, and that's not 1. But this idea was right, in that if you subtract... So when I first looked at this, I realized, oh, it's going to be this minus I over n plus 1 over n, which was a weird way, but I think that's how I first wrote it in my notes when I was doing this pattern finding. And I saw that it worked for all of these. And then I think I wrote it many different ways. I think I wrote this, it got a common denominator. I don't know if that was helpful. The slope would be the connecting these 2 points, I over n. Shoot, I'll have to edit that a little bit. I over n comma 0 is this point. And then the other point is 0 comma n plus 1 minus I over n. And we need the slope between those two. I know this is the challenging part. Okay, so we're going to do that n plus 1 minus I over n minus 0 over 0 minus I over n. And that simplifies a whole bunch, n plus 1 minus I over I, just like it did in our examples. I think at that point I simplified it even more and wrote it as n plus 1. Yeah, multiply top and bottom by n. Oh, well, this should be a negative I. That's why it's looking funny to me. So I rewrote this as n plus 1 over I. You can see I'm still trying to make errors in this. Of course, I checked my work against an online solver because I don't trust myself anymore. And I did visuals of this. But that's what I got. After some work, that's the slope. But we can always check it. You know, you could plug in and find what that first slope was. And then this is the intercept. N plus 1 minus I over n. Whew. Okay, so that was challenge number 1, was just to formalize what these lines are. But I just had this feeling that if I could find the equations for those lines, then I knew what I needed to do next, which was find the intersection and then think about what happens when n goes to infinity. And I realized at this point I do have the slope. This is the slope. Now, it's not necessarily the tangent slope. It's the slope of one of these lines. But if you've done calculus before, you know that is that you're going to take the limit. That's going to approach the slope of the tangent line. So I had a few thoughts here. I had this thought that maybe the slope is going to be 1 minus n plus 1 over I. But my first observation, I kind of discarded that because I was like, but there is not even an x in there. So I don't even know how to make sense of that. But then I realized I just need that intersection point, which is basically what happens if you take a given value here, like 1 or 2 or 3, and then plug in the next value and find the intersection. So here's what I did. I said, what if I have a given value? And again, there's probably a much better solution out there. And then I look at the next tick mark, which would be an I plus 1 here. And I solve for x. I knew it was going to simplify a lot because I'd done small examples already. You can multiply everything by n. This may be a daunting task for those people that are scared of algebra, but I just needed to get the x's to one side and simplify. When I was all done, it came out to be I squared plus I over n squared plus n, which was kind of satisfying when I simplified it all out. I checked that against an online solver later and was happy with that it matched up. Thank goodness. But I could also just check it against my examples, like what is that first intersection point? Well, let's see, if I plug in a 1 for the I, it's going to be 1 squared plus 1 over 5 squared plus 5. So it was 2 over 30, or 1/15. And I could see that that's what it was in my visuals. Okay, so at that point I kind of was like, okay, I think I've made it through the worst of it. So that was all pre-calculus, but it involved lots of labeling. So now was the challenge of how do I put all this together? And I thought about, the more you think about a problem, you just add a little bit here or there. And then maybe a week ago I was going to bed and I was like, well, I want to know what happens to this as n goes to infinity. So the part that was confusing me was these i's. So I thought, can I get rid of that I? So there's only n's and x's. And then I realized, I can solve that. This is one of these equations that would just totally freak out my students. But if the question says solve for I here, but it's a quadratic. Part of the problem with sometimes using the quadratic is we are used to using an x. But if you get one side is 0, you can have I squared, and the number in front of it is 1. Then you're going to have I, and the number in front of that is 1. And then you're going to have minus xn squared plus xn, and that's like my c. That bothers students. This is like a, b, and c. And you get to sing the quadratic formula. Negative b plus or minus square root b squared minus 4ac all over 2a. So it's negative 1 plus or minus square root b squared minus 4ac. So b squared is 1 minus 4ac, and that has a negative, so it's going to end up being a plus 4 times all this. Xn squared plus 4xn all over 2a. You can think about it, but x has to be, let me be careful here. Yeah, we're dealing with positive x's, so in order for x to be positive, we need the positive root. And at that point, I was really happy because we now have landed in a Calculus 1 problem. And what I mean is this. The function I was still doubtful of my work, but the function I want has to have the following couple properties. So one property is that its slope has to be the same as this slope as n goes to infinity. Because the slopes of these lines and the slope of the curve should be approaching the same thing. And then I can replace I with this thing. So then we can write the limit as n goes to infinity of 1 minus n plus 1. And then we have this 1/2 negative 1 plus the square root of 1 plus 4xn squared plus 4xn. And I'm not scared of limits. Now, this is part of why I decided to make a video on this, is because these sorts of limits really scare my students. If you're doing a limit at infinity, I do have other videos on this, and I hope to teach Calculus 1 next year, and I'll make more. You need a specific strategy, which is to rewrite things in this form, 1 over n squared, because we know those go to 0. So when I look at this, I go, okay, the thing that's confusing me is this n, because it's going to infinity and that's going to infinity. So I'm going to rewrite it in a funny way. If you don't have this strategy or have never seen it, you wouldn't know this. But if you've taken Calculus 1, you would, to multiply top and bottom by 1 over n. If all you have is L'Hopital's rule, it's not going to help you on a problem like this, or it's going to make it much worse. So I think, and I think at this point I just wrote the answer because I've done so many of these limits. And that's not because I'm smart, just because I've seen a lot of these. So 1 plus 1 over n. I'm pretty sure I flipped the 2 and put it up here. And then the rest was somewhat routine. This is a question we could ask on a final in our Calculus 1 course. There's one challenge here, which is how in the world do we simplify this? But if you've taken our calculus courses, you've seen this before. And the idea is to get the end under the radical. So beginning with a positive n, we can just write the square root of this squared. And it all simplifies down to 1 over n squared plus 4x, because the n squareds cancel, plus 4x over n. And that's just to help you analyze it. Because the moment you've done that, you can see what the answer is. This is going to go to 0. 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 So all you're left with is the limit. Let me get back to that blue. The limit as n goes to infinity of 1 minus 2 over the square root of 4x. And the square root of 4 is 2. We just took the limit. So it's 1 minus 1 over the square root of x. And that's where the Calculus 1 student helps us, was doing that limit. So now we can say, all right, f for the function we're trying to find, f prime is this. And since we're doing calculus, let's rewrite it this way. Then you go to Calculus 2. So there was our Math 124 skill, this limit. Now for the Math 125 students is, you know that if you know the derivative, you can take the antiderivative, so the power is going to become positive half, and you're going to flip it, and you're going to write a plus c. So there's our Math 125 moment. But then the good Math 125 students would say, what is c? And there's a couple points we know on the curve. When you plug in 0, you get a 1. When you plug in a 1, you get a 0. So those are our initial conditions. So you can say f of 0 equals 1, and we have our function. So that solution was kind of a fun tour through a particular skill from Calculus 1, a particular skill from Calculus 2. I'll show you some visuals, and then I'll talk about something else that came up as I was looking at it. So here's the visuals. Here it is with just a few strings in pegs or rubber bands or whatever. I'll talk about that point in a second. That's just the first intersection point there. I mean, after the very first point. Okay. So let's look at it and see what happens if I increase. So the red curve is the curve we just solved for. And these intersection points are getting closer, and the slopes are getting closer. So I keep going. Now if I let this go too much, it starts to have trouble because it's drawing a lot of stuff at once. There you go. It approaches that way. Now what I was unsatisfied with as I was checking my work was, yes, it appears to be approaching it, but even at 30, there's a pretty darn big gap, which made me doubt my work. And so that brought up another interesting calculus question, which is, can I describe this error? Now, as I made it really, really large, it got close. And so I just thought, I'm just going to analyze the error at one point. Meaning I'm going to compare, let me plot this other thing as well, 2 over n to the second plus n, comma. So I'm going to grab this. Should have that ready. And let's do the same thing here. Okay, I'm going to compare how far apart those are. So for, like 6 of these lines, that error is pretty big. 7, it gets smaller. 8, 9, 10. It's still pretty big, I felt like. I was a little unsatisfied with this. And I was just looking at one point, how close they're getting. But I did see that it was shrinking. And if I went to like 300, they do eventually get closer to closer together. It's just pretty slow. The computer starts to run into trouble. It's because I'm graphing these. See if I get rid of that. So it does approach, and at that point I was like, okay, my solution is approaching. It just approaches really slowly. Okay. So that does suggest maybe there's a better solution that approaches more quickly. But that made me think, hey, this is a chance for me to explain error bounds. So what I did is, this point's coming from that intersection. That's that I squared plus I formula we had. It doesn't matter. But I want to compare this, the y value, and this. And I just shoved that into Mathematica. Here's the online version of Mathematica. And I said, what's the difference between those? An interesting thing happens. I didn't include the 1 because it canceled. So I said, what is the difference between those? And it tried to simplify. It tried to tell me everything it could about the difference between those. It said this. It said, yes, it's going to 0. Okay. It talked about a whole bunch of things. It tried to do a series expansion, which is not a very good one, at -1. It tried to do an expansion at 0. That's great. That's fine. And then I saw this and I was like, ooh, that's helpful. Why is this helpful? This is actually called the Laurent series, but it's a version of the Taylor series. So this is for my calculus calculus 3 students, or students going into calculus 3, which said, okay, if I take this thing and add this at a given n, this is sort of like the error. Now, if n is like 10, then this number is going to be pretty small because you're dividing by 10. This number is going to be really small because you're dividing by 100. This number is going to be extremely small because you're dividing by 1,000. This is going to be even smaller because you're dividing by 10,000. And usually at some point we say, and then things of even smaller order. This is called big O notation. And those are helpful when you're doing asymptotics. And people do this all the time. It's a very valuable part of Taylor series, is because they can allow you to take anything and then give an approximation and then chop it off. If you can set it up just right, maybe you can set it up so the errors are getting really small. So at this point I was happy because then I could see precisely when n goes to infinity, these were going to 0. It just was slow. This is a pretty slow error term, as we might say right here. But you could attach that onto your function. So 2 root 2 minus 2 over n. Here we go back to our pegs. Let's make n kind of small. And maybe I'll just draw one of these because it starts to get pretty messy. So there's our function. Now the problem is if you just add it to it, you are going to make the error worse elsewhere probably, because I was just analyzing one point. But let's analyze this one point and say, what if we add... Where's our function? That first error term, which was 2 root 2. I think it was minus 2. No, plus 2. We'll go look it up. Over n. It must have been minus 2 because that's not close. Okay, so there's with that. Let me copy it and remove it. There's without it. So there's, and if we add that little piece on, ooh, we're like right on. So you can see I did a really good job of estimating the error there. Now, the error elsewhere has gotten a little worse. Excuse me. But if you add the next term, you're going to be really close everywhere. So it's square root of 2 over n squared. The reason I know that is because n squared is going to be so small even for a relatively small number like 18. Now, the error is still going to be bad elsewhere, but this is going to approximate it much better as we approach. So I feel like that was a much nicer picture than my original one, without the error bounds on there. So I just thought that was kind of a long extra bit I threw in there, but I was just unsatisfied that it was lower. And it's always good to ask the question, why is it lower? What can I say about that? But it does approach that function. Okay, I then, since then, have thought a little more about this, and I was like, well, how do I actually set it up to make a certain parabola? But I realized this video is already going to be long enough. So I don't know if I'll do all of these, but I have other parts lined up to maybe discuss. Again, I have a new quarter starting, so I won't have a lot of time for this. But if this interests you, let me know in the comments. Say, I would like to see part 2. Because in part 2, I was going to talk about what if you wanted to make 2 lines that are going out of the origin like this. And my goal was to try to make a certain parabola. And then in part 3, I could talk about how do I actually fit it to a parabola, which I think could be interesting for an art project. If you were trying to make a certain parabola, how could you do it? But there's so many questions to ask. It's hard to know what the next best question is. And certainly a lot of those questions have been asked online. But if you'd like me to go further, let me know in the comments, because I need that little push And if you do say, I'd like to see those other parts, I'll do them. All right. Thank you for listening.